study, but I highly, highly encourage you to make sure you can do your own spreadsheet on your own without having to look at mine for the solution, because you will get very much punished on the exam if you do not understand conceptually everything you're doing with the spreadsheet. And I want you to be able to look at this and understand that you go from a guess of curvature to iterating that depth of the compression region. But for a given iteration, you basically look at the strain, stress, force, and moment contribution from every one of your fibers for every one of your materials. If you double count materials, there's ways we talk about for taking that effect into account. So I'll be looking for your conceptual understanding of that, because that's kind of the big thing out of this. My guess is that most of you will never actually program a moment curvature analysis by hand like this in Excel ever again, because Excel is not a good program for doing moment curvature analysis. But those of you who are doing it, you'll probably use a program like Extract. Extract is the most common moment curvature analysis program as far as I'm aware. And you should understand very intimately what that program is doing, because you're talking about doing a very complex nonlinear analysis. And if there's things that are wrong or things that are misbehaving, you have to be the one to make sure that things are working correctly and catch and correct those errors. So it's not like linear elastic analysis software. You can just tell the computer to go, and it's using very well-defined parameters, and there's not these big changes in stiffness and matrix issues that are going on oftentimes. So you don't have to worry about a lot of stuff. But in this stuff, to be doing nonlinear analysis, you really have to understand what's going on. So that's what I'm looking for, is do you understand the process of how this problem is being solved? Make sure you understand that at a very good level conceptually. And that's why I did the hand calc on it. That's why I spent essentially 2 weeks on this problem. But I budgeted some time if you guys have any other questions, so we could talk about that. Make sure kind of everyone's at least making progress on it. Don't feel ashamed to ask questions. I'm sure many of your fellow classmates have questions too, given the feedback I've gotten in emails. Everyone's good. Yes?
What exactly are we supposed to graph? I was kind of confused.
So I want you to generate, essentially, a graph of the moment contributions of each of your materials, and subsequently the entire cross-section, versus curvature. So for a given value of curvature, what is the moment in the cross-section of that? Okay? Because from a conceptual point of view, essentially what you're doing is this. You've got a column. And you're pushing on this guy, say lateral. We're not doing everything based off this, let's say, lateral force though. Whatever that force is, it is. Instead of looking at, let's say, this force versus the moment in the cross-section, we're looking at instead say if this thing bends out, this section will have a given amount of curvature, right? So it'll have a curvature profile, and that's what we looked at with these slides here, right? You could look at the curvature of this cross-section. So you could look at, let's say, the height versus curvature, and you come up with, then, if you're looking at, say, h versus curvature, it looks something like this. You're looking at, let's say, one of these cross-sections of interest. Generally speaking, you look towards the base, because that's where you have the maximum moment and the highest level of curvature, right? So you generally want to look at, essentially, this cross-section way down here. But that can depend on your column. We're just looking kind of a cantilever column being pushed over. You can have a column, let's say, between the ground floor and the first floor of a building. That column may be in double bending, in which case you want to look at, let's say, both sides of this. So you want to look at the middle. There's reasons to look at different aspects of this. But in our case, we're just going with very simple stuff because we want to try to keep the class simple so that you're getting concepts, and then on your own, you can do, let's say, further research on this stuff, and you can teach yourself more complex stuff. But you're essentially looking at the base of this and saying, okay, how far I push this over is going to give me a certain amount of curvature. And how much curvature I have is then essentially related to the moment being generated from this V load. Right? So you're going to get a reacting force down there but you'll also get a moment. So you're then looking at plotting this moment versus the curvature at the base. Right? So that's what your analysis is doing. So as you're stepping through curvatures, you're basically looking at how far has this column been pushed over. So as you're pushing this over more and more and more, you start getting, instead of having linear elastic behavior, you get this nonlinear curvature forming. And you want to know then, as I'm going nonlinear and getting this nonlinear deformation, what's the moment associated with the given amount of nonlinear deformation? Right? So that's why we're looking at moment curvature. So you know, let's say, a given guess of curvature. That's something you're interested in, let's say, iterating from step to step. You look at curvature when there's zero load, and you look at curvature as your loads are increasing. And then as you're doing that, you're backing out what's the moment capacity of this column for that level of curvature. And then you want to generate, essentially, this plot right here. And the reason this was interesting was because once we get this moment curvature response, we can look back to this again. We can say, well, if I get the area under the plastic curvature region, if I integrate curvature with respect to distance, I get slope. And so if you integrate the plastic curvature, you therefore get plastic rotation. And once you know plastic rotation, you can take that and translate that into structural analysis. And then, let's say, as we get to the next part of the class, we'll do a pushover analysis. You can then directly relate this plastic rotation capacity to, let's say, the capacity of your frame. And then that's where you'll get, let's say, this force V required to push this over. Right? But you're not necessarily interested in this force because how this behaves with respect to curvature isn't necessarily dependent on this particular system with this force right here. It's kind of generic. So you're saying, well, for a given level of curvature at this cross-section, I'm going to get this response. And so you can then take that kind of generic point of view and put that in specific structural analysis models. And that's where we'll be going after this. Yes?
Are you going to be going over plastic hinging more as we go on?
Yes, that's the next part of the class.
I'm not going to. My question won't be answered then. So.
Right, so we'll talk about then taking this plastic hinging concept and implementing it into analysis models. And we'll do by hand, pretty detailed example, and then we'll also move into doing computer programming with that as well, in SAP specifically. So you'll see how everything, hopefully once we do that, everything will start falling into place, and you'll understand kind of where you're going. You start with materials, you work from the material point of view to essentially this cross-sectional point of view, where you're looking for a given amount of curvature at this location in a cross-section, what's the moment? And then from that, you can then take that capacity essentially of your section, you can plug that into your analysis models, and then you can do, let's say, analysis of your frame with your beams and your columns. You've done a moment curvature analysis for all your nonlinear elements. And when you plug that into your model, then you can in fact determine capacities of things. You can say, what's the displacement capacity of this frame? What force is required to push this frame over? And then obviously you can correlate that to, let's say, your design stuff. We talked about the code design. You can then compare, let's say, with your design forces as you're pushing this over, you know, what are the resultant curvatures and rotations and such in your column, and are they satisfactory, right? You can check to see, did this frame exceed its plastic rotation capacity? And if it did, obviously you would go back and change your design. If it doesn't, well then you verified your design is working correctly. That's stuff that we're going to next. In terms of just the moment curvature analysis process though, any other questions? Does everyone understand? I probably didn't explain this too clearly, I realize after the fact. Does everyone understand why you're iterating? And when you look at the force in the section, you're taking your strain, you're iterating this to equal the axial load of the section. That's equilibrium, right? Sum of your forces is equal to 0. So you're just doing it a different way. The way I kind of wrote on the board initially was you take this, take the sum of those forces, let's say minus your axial load, and then you iterate this to 0. Just rearranging the equation to solving for axial force instead of solving for 0. That's just generally the way it's done, because the axial load on the section plays a big deal for moment curvature analysis. We can take some more time to talk about this if you guys like. The one correction I sent out on the announcement was going through this on last Wednesday with you guys, I mentioned there were 4 fibers. At the time, that didn't look right to me, and of course, I missed finding that central fiber. But you should have 5 steel fibers. You have 5 bars. What I was trying to say, and probably did so poorly, was that this central fiber here, at the very middle of the section, if you look at the moment contribution of this set of steel fibers, it's always 0, because your moment arm to the center of your section, in this case, is going to be 0. So those bars don't contribute at all to the moment capacity of the section. But even though they don't contribute to the moment capacity, you should still find that they have force. So you need to take that force into account for equilibrium of your cross-section. So those have to be included. Yes?
Can you please show once again how you use the solver?
Sure. So for solver, you want to iterate this value of strain that you're guessing, right? And you want to set this equal to, or iterate the strain such that this total force is equal to your axial load on your cross-section, right? That's equilibrium there. So if you have some initial guess, say, what I recommended is always guess the step before. So if you wanted to do this step by step, you'd always say, well, in this next one, I'm guessing the step before. You always guess the step before for your first guess. Right? But you'll see that if I use the step before, is my first guess, and I look at the force on the cross-section now, you'll see that this force here is not equal to the axial force on the cross-section, right? This is now equal to, let's say, 700 kips positive in tension. This should be equal to 600 kips compression. So what you want to do is you want to tell Excel, I want you to change this value of strain such that this cell is equal to the axial force. Right? So if you use solver, you go to data, solver, and if it's not showing up, you want to go to your options, cell options. You want to go to add-ins, and you want to make sure your solver add-in is installed. I think most Excels install this automatically now for 2007 and on, but if it isn't there automatically, you can just go in and add it in manually in the add-ins. So that'll make it show up if it's not there. But if you go to solver, Excel will ask you to set a target cell equal to a value. So in this case, I'm going to say, well, I'm interested in setting this force equal to the axial force on the section. In this case, it's minus 599. By changing what cell? Well, I want to iterate the compressive strain right here. So you then click solve, and it tells me your solver found a solution. And when you look back out here now, it's changed this value by iterating it by an algorithm, iteration algorithm, such that this force here now is equal to this axial force. Does that make sense? So then you just do that for every interval. This is one of the reasons Excel is not too handy for this sort of analysis, because ideally you want to have this automated, right? You wouldn't be clicking iterate for me every time. You set this up in a computer algorithm where it would do all your fibers and all your curvatures and all your iterations automatically just by clicking the button. But Excel still can be used for this stuff, it's just tedious. But that's the idea. You're iterating this compressive strain by basically changing the depth of your neutral axis. So let's say your first guess is a profile that looks something like this. So you've got some epsilon c, the depth of your neutral axis. This is value right here, c. So that's what I have on one above the columns there. For a given increment, you have a known curvature. And if you draw out the light triangle here, you can easily solve for that depth of your compression zone. See? Right? So you'd have this relationship for small angles where you say this angle is approximately equal to the tangent, and then you'd say this is equal to so on C over C. So you can easily rearrange this equation and solve for C once you have your initial guess of your depth of your compression region as well as your curvature increment. And so then what you're doing essentially is you're moving this profile up and down, right? This curvature is a constant for your given increment, right? Your curvature doesn't change. So by changing the depth of your compression region, let's say, you may go down, for clarity's sake, and have your next guess be like this. And you'll see that like this. You have, let's say, your different guesses, epsilon C1 and epsilon C2. And what would happen then is you'd get, let's say, a C1 and a C2, because you're changing how much compressive strain is in the kind of the section as a whole. You're moving this profile up and down as you're iterating. So you're telling Excel, basically find me the balance point where the amount of compression generated from the strain profile is equal to the amount of tension generated by the strain profile on either side. Does that make more sense? Yes?
I know you talked about this like many times, but how do you figure out what curvature you want to work? I know you said
It's up to
it
you.
is up to us, but
So I gave you some recommendations,
Yeah.
just the empirical stuff that I've seen posted in literature before. It's really just kind of up to you. But the way I proposed doing it, I believe in here, was you look at your yield strain of your steel, and you divide that by the depth of your section to get the same unit as curvature. This is kind of an empirical way of looking at it. Because curvature has units of length to the -1. So let's say inches to the -1 or meters to the -1. And this gives you that correct unit. And you're kind of normalizing it based off of section properties. So there's lots of stuff that goes into moment curvature analysis I've seen nowadays and try to get everything normalized parameters. So it's not even really a moment curvature analysis anymore. It's kind of different parameters that are normalized by other parameters in the section, but I'm not going to go into that. But I just recommend in this case that you pick a delta based off some logical framework. So you know, let's say, the yield strain of your steel, you know the depth of your cross-section, let's say that's a good delta. And so you'll look at this given delta when you're below, let's say, a certain threshold, and then when you pass that threshold, then you go to a different delta. Because the idea was we get good resolution on this curve here. Right? If you have too few points, you won't get the full resolution of, let's say, this elastic region, and then going to the nonlinear as you pass your, let's say, your yield point. If your mesh, I shouldn't say your mesh, but your curvature increments are too small, let's say you can miss your yield point there. So you don't want to have that happening. And make sure you pick enough curvature increments such that you can get this full profile. And then there's ways to idealize the whole curve after that. So in this case, I had a trilinear idealization here. But that changed for some reason. Oh, and I had the fifth fiber in, I forgot to rechange that, but that's fine. But you could come up with different idealization models for this. And there doesn't always have to be, an empirical equation for that idealization. Like Caltrans generally says, do a basically elastoplastic, essentially, moment curvature analysis, where you come up and then just go straight over. So there's different ways of doing it, depending on what field you're working in. Yes?
At the top, and you're given information,
Yes.
you have the transponder area.
Yes.
You're calculating that in order to be able to subtract that out?
I'm calculating that because I want to know what's the initial strain on the cross section to start out. Because this section doesn't have zero load. It's not this section floating in space. It's got a load when there's no curvature on there, right? You've got some dead load on your column. In this case, our dead load is equal to 600 kips compressive force. So you've got some initial load. That initial load is going to cause initial strains. So it's not too important, like you may say, well, it doesn't really matter for this monotonic analysis. When you do, let's say, cyclic analysis, you always look at the previous step of curvature for your strain states. So when you're doing, let's say, full dynamic analysis with actual earthquakes, you can't ignore, let's say, that first step when you have initial strains there. Because as your analysis goes, it's going to be keeping looking at the step before it for strains. So this is for getting the initial strains in your cross-section. So you have multiple materials. In order to get that initial strain state, you need to look at your steel and you need to look at your concrete and say these guys have different moduli of elasticity. Therefore, I want to convert these to be equivalent. So if I take the force divided by the area, I'm using kind of the equivalent area based on the modulus of elasticity of both materials.
Yeah. Okay.
And once you have that equivalent area, you get stress is force divided by area. Then you can get your strain from that. Once you know stress, you now have your equivalent modulus of elasticity, so you can get strain. And then once you have that strain, you can get that strain in all your fibers. And therefore you can get the stress and so on and so forth for each of the individual fibers. So you're starting with global, you're going down kind of the smearing of this flow behavior of everything, and then you take that global and you make it local again by looking at each of those fibers. And you can do the same thing for, let's say, initial bending moments on the cross section. So your bending moment would be MC over I, and there's transformed I as well. So you have, let's say, the I from your concrete, but you also have the I from your steel, and you can transform that I to be an equivalent I. And ACI details all that stuff in detail for kind of methods for doing that. But that's more like a reinforced concrete sort of thing I'd cover. Not so much here. Any other questions? Is everyone good? Hopefully on finishing this. I know it's kind of a big spreadsheet, but hopefully you'll get a good understanding of everything that's going on in it. Even though it's really intimidating, like I said, just be slow and methodical with it. Don't look at it in terms of this big, massive behemoth that is really difficult to deal with. Look at it section by section. So start with, let's say, your unconfined concrete, material number 1. For material number 1, you want to get strain. So break it up to strain in each of your fibers. Once you have that strain in that fiber, calculate the stress in that fiber. Once you have the stress, calculate the force in that fiber. Once you have the force, calculate the moment contribution of that fiber. And then move on to your next materials. So it doesn't really matter whether you have 1 material or 15. You can do this analysis process the same. So what I want to cover now is basically doing a moment curvature analysis in SAP. And I'll be, like I said before, the first to admit, SAP is terrible for moment curvature analysis. I don't really care for it, but we don't have extract available here at SDSU, so we have to work with what we have. And that said, even though SAP is terrible for the moment curvature analysis, in my opinion, SAP is really nice for, let's say, the pushover analysis, which uses this data. So I want to kind of get you guys familiar with just kind of SAP's interface a little bit. And as we move on to the next part of the class, for the next section, we do pushover analysis. You'll see that you can do pushover analysis by hand, but you can also do pushover analysis in SAP. And you'll take a lot of these moment curvature analysis results, and you'll put them into parameters that SAP will use for doing different analyses. So if you just start a new file, so when you open up, SAP will ask you for a bunch of different types of things. In this case, for the moment curvature analysis, we don't care about kind of the big picture. We're just interested in looking at a given cross-section. So you can pick essentially anything you want. You can pick a beam, start it off like this. Grid. And so we're not going to care too much about what SAP's doing here for now. We will later when we start building and pushing over frames. But what we're interested in is defining the materials in defining the section properties of my cross section. So define frame sections and define materials. Okay. So you need to give SAP, in this case, all the material properties that are of interest to us. So if you recall from your homework number 4, you came up with equations, essentially. Right? If you look back at any one of these stress fibers, you've got an equation there, Mander's equation, let's say, for this concrete, for confined or unconfined or steel. And from that equation, you could get points. And so all I did for here was I just picked some points, and I got, let's say, 10, 15 points for each of my different materials. So instead of using, let's say, this equation and defining 8,000 points like we would have with our test data, I'm picking a small, reasonable number of points that would define this curve real well. So all I did for this is I picked points, and I plotted these on the actual curve with a whole bunch of points, and I saw, well, these points give me essentially that full context of that curve as good as I'm going to get it without having to be absurd with the number of individual data points I'm using. So these essentially are just different materials that I'm going to be using. So I have the stress versus strain behavior for each of these. And I copy these essentially over into SAP. So the way I did that was define materials, to add a new material. And so SAP will ask you for material type. So in our case, we want to make sure we have concrete and rebar. So the mistake that you don't want to make is picking steel, because SAP doesn't recognize steel for its moment curvature analysis. So it's just kind of internal quirk with the program. If you use steel, it won't ever show up as options for you to choose. So you want to use rebar. So this is just, doesn't have to necessarily be steel, but this is just reinforcing bars for moment curvature analysis. So let's say we're going to start out with steel. I want to, let's say, have a user rebar. You can have defaults in here that you can load in. SAP has a default for ASTM 706. We actually had test data for a bar, so instead of using 706 or 615, which are the two major types of rebar, we're going to use a user define. We can call this, let's say, A706. Can I zoom in on this at all? I don't think I can. I can make screen resolution smaller. So. See it better? Is that better? Okay. So we can just call it, let's say, A706, number 11 bar. In this case, I want to go to Advanced Property Display. Didn't save that name. You want to go to Show Material Properties and go to Show Nonlinear Material Data. So SAP oftentimes will let you use its inbuilt equations. So it has, let's say, inbuilt steel models based off of essentially these properties here. I generally don't like using that stuff. I like to know exactly what it's doing. So I'm going to give it a user-defined stress strain curve. And so this is where you can put in your data. So I just picked some points here. I have a total of 11 points. So I can just copy my stress strain data. Tell SAP I've got 11 points in the curve. And just essentially copy and paste my stress strain data in. And then SAP will generate that curve for you. Okay. So all I did for this was tell SAP I've got 2 points in my compression region. I've got linear elastic, I yield, and then I'm elastic after that. So elastoplastic response. This is the best way to model, let's say, buckling behavior very, very simplistically. And then for the tensile region, I just used Mander's model for steel, and I picked 8 or 10 points, so that I'm capturing the linear elastic region, I'm capturing the yield plateau correctly, and I'm capturing enough points on the curve. You can see that matches overall pretty well. So SAP shows you kind of a plot here as well. Zoomed in what that looks like. I believe I used a modulus elasticity of 28,500 for this deal. And so you don't have to worry about any of this stuff because we're not using SAP's internal models. It's just going to use now, whenever this material is loaded, the stress strain data that you defined here. So SAP also has things inbuilt for doing Mander's model for concrete. I will be the first to admit I did not figure them out because I would do Mander's model on my own, and I could never get SAP to simulate Mander's model based on the unconfined concrete. So what I did is I just put everything in here by hand. So I'm going to add another material. This time, instead of adding rebar, I want to add concrete. And I want to use a user-defined concrete once again. So I will call this, let's say, unconfined concrete. Show material properties. I'm going here to my nonlinear material data. Once again, instead of using parametric. So ideally what SAP I would do for you, if you didn't know any better, was you give SAP your f prime of C of your unconfined concrete. It would then use the detailing in your section that you give it in the section generator, essentially, those values and those parameters, and it would develop Mander's model for you. But as I said, I don't trust SAP, and I can't get it to give me back what I know should be correct. So I just go to user defined once again. So I did the same thing for my unconfined concrete. I have 12 points here, so I can just copy my stress strain data over. SAP, I have 12 points. And now you can see I have 0 tensile capacity of the cross section. We're still modeling 0 tension in the concrete. But now I've also got the compressive behavior fully defined here as well. And so I want to change the modulus plasticity of the concrete as well to match that value, what it should be. In this case, it's 41. This doesn't have to be changed, but 5.2 KSI was the expected compressive strength of the concrete. Right? 4 KSI would be the nominal, but we want to use expected values. So 5.2 KSI would be the expected compressive strength.
Likewise, we're doing the expected yield strength in the homework 5, we use 68 KSI.
Yes. Or in the case of our rebar, I think it's actually like 72 or something from the test data.
Oh, okay.
Right? You want to use your actual test data. So Caltrans, if you use those guidelines, they basically say if you don't have any test data available, these are the acceptable values to use.
Gotcha.
But then you do have test data available, so you want to use the specifics of your test data.
Well, we got more.
Right. And so realistically speaking, in most projects you do, you probably want to have, let's say, a suite of bar tests available to you of the steel that's going to be used in your cross section. So I say just use the standard nominal values, bump them up to these expected values, and go up that. But if you're doing, let's say, a sufficiently large project, it may be of interest to make sure that you do lab tests of your materials. You may do a test of 5 or 6 different rebar that are going to go into your cross section. Make sure you have, let's say, the appropriate stress strain profiles for your longitudinal bars, your transverse bars, et cetera, et cetera. It really depends on the project. So once again, we want to do one more concrete material, and this time it'll be our confined concrete. This came out to be 7.3 KSI, like 4,800. Modulus elasticity. So I can go to my nonlinear material data. Instead of using Mander's model, once again, I use user defined. 12 points. And I'll pull off my
quick question.
Yes.
The point that you picked up, they are independent of each other, right? They're not at the same curvature value.
These are just the material stress strain behaviors. They don't care about curvature whatsoever. This was, let's say, from homework 4. So I didn't even get to homework 5 yet.
So what I'm saying is the point that you pick for each material is independent of the other.
Yes.
Okay.
Yes. So you give each material the stress strain response, just independently of the other ones.
Okay.
That's all we're doing. Verify we have the right plot. Looks okay. So now I've got all my materials defined. So what I can do is I can go to Define, Section Properties, Frame Sections. I can add a new property. If you go down here to Other, SAP has this option for Section Designer. So this is where you can do moment curvature analysis. Go to Section Designer. You can pick a base material. I pick my base is unconfined concrete. And here you can also change different aspects of your cross section. So you can do a moment curvature analysis, but then you can, let's say, manually adjust things if you need to. Let's say changing your cross-sectional area, changing your moment of inertia. It'll auto-calculate those from what you have, but sometimes you want to override those because you're simplifying the model, let's say. So if you go to your set modifiers, it lets you scale these properties as needed. So if we want to go into the section designer now, we'll go so. So to start out, you get a blank template. And so in this case, I'd want to draw. And I have a rectangular section, so you can draw things more complicated in SAP if you want to using segments and sectors. Realistically speaking, you wouldn't want to use SAP for anything non-simple anyway, just because the moment curvature analysis here is awful. But for simple things, it can still work. So we draw a rectangle like so, just by clicking the center point. If I right-click on this now, you'll see I have a bunch of options. And it defaults this to unconfined concrete. So I can call this unconfined concrete. You'll see now it lets me define a center point, so I'm centered on 0, 0. That's fine. That's just relative. Then I can also define section value. So it's a 48 by 48 inch section we're looking at for this homework. And you may be tempted to use reinforcing here. Don't do that. So this is for if SAP is doing it on its own for you, and this is where I run into a lot of problems trying to get it to work. It tries to do its own thing, and I have no idea what it's doing, and therefore, if you don't know what things are doing, you generally should avoid using them. So we can get around that by doing things manually, but you don't want to put in reinforcing here or else it'll cause things to be messed up. So you can verify you have the correct concrete model by clicking on concrete model, and it shows in here you have unconfined concrete, and it recognizes your maximum strain and your ultimate strain. So what I want to do next is I want to draw the confined region of my concrete. So I can draw solid shape again, rectangular, on the center point. Right click this again. I can call this one confined concrete. And now you can go and select your material, and I'll click confined concrete. I like to give it a different color. So let's say red. So the height and width of this now would depend on the height and width of your confined concrete core. I have the solutions for this. It is 43.5, essentially 43.6. So you can do 43.6. 43.6. Okay, and now you've got essentially your unconfined concrete shell, and now you've got your confined concrete core in the middle. So what you want to do next is you want to add rebar in. So you can draw a reinforcing shape, rectangular pattern. Click on the center there, and it predefines a bunch of bars for you. So you can change these by right-clicking here. Define the material. A706 number 11 rebar is what I wanted to use. That's selected, so that's good. And then you select the dimensions, essentially, of the center lines of these rebar. So I want to say 44.6 or something like that. I think that's correct. Close enough. We'll go with that. So once you have that, you can click on the sides of this. And so if you click on, let's say, this bottom edge, you can see it's flashing. And this lets you tell SAP all the information you need to know. So you have number 11 bars. So it lets you pick your default bar sizes. It tells you the area of that is so. And your bar spacing, in this case, is 10.9 inches on center. You can click Apply to all edges. And so now you've got a set of rebar like so. Click here again. Our bars on the corners now. Right, you can see this corner is flashing. Number 11s, apply to all corners. And there's my outer ring of bars for this cross section. Now I want the inner ring of bars, so I can draw once again, reinforcing shape, rectangular pattern. Put those in the middle. And the dimensions of this, I believe, are 22.8. What to say?
21.
The 21.8?
10.9 times 2.
Yeah, 21.8. So we can then change the outer edges again. So number 5s, I want number 11 bars. Bar spacing is 10.9 inches. And out here, the corners are also number 11 bars. So those aren't matching up. I think there's a little bit of difference in here. Yeah, it's saying 10.2 for some reason. So I need to add, I think, 1.4. Not sure why SAP is doing that. I think it may just be where it's defining those bars. I think it may be to, let's say, the outer edge and not the center line. But yeah, so 22.2. Check that. Now if you hover over each of these rebars, you'll see the center, the X point down here is now 10.9. So it just takes a little bit of playing around to figure out whether it's going to center lines or to outer edges or whatnot. I think it's going to outer edges instead of center lines, so that's why you go, let's say 23.2 instead of, or 21.8. So now we've got the rebar in our section well defined. And so we can tell SAP to define a fiber layout. And so the 2 direction is, I believe, this direction right here. 3 direction is up and down. Maybe it's the other way around. But you can easily play around a little bit. So I used 48 fibers for the homework solution, so I want to do the same thing here. I can tell it calculate moment curvature using fibers. It's also got this direct integration approach that I don't particularly understand how it gets its results, but I like using the fibers. So calculate moment curvature using fibers. We have 28 fibers in that direction. We'll now do the meshing. And you can see it's now meshed this guy up based on your confined concrete core and your outer shell. And I've got a total of 48 fibers as you go from left to right. So you can also do moment curvature in multiple directions. It doesn't have to just be one. So in this case, we're saying, well, as you're pushing it over, I'm looking at the bending moment in one direction. But a lot of real structures, you'll have bending moments in 2 directions. And you can do the same thing in terms of analysis. Instead of just iterating one side going up and down, iterating the compression region on one side only, you'd iterate on both. And so if you need to mesh in both directions, SAP can easily do that. So you can just define your different mesh sizes in multiple directions. In this case, though, we only care about the mesh sizing in the one direction of interest here. So now I can go to this button up here, show moment curvature curve. And you will see it has an exact integration curve and a fiber curve. Like I said, I'm really not sure what SAP is doing for the exact integration curve. I would imagine that your fiber curve should give you back the same results, but it doesn't, so really not sure what's going on there, but that is what it is. So I don't look at the exact integration curve. I'm interested in the fiber model curve. And you can look at different things here. You can look at moment versus curvature. You can look at neutral axis depth versus curvature for different levels of curvature. You can look at steel strain, concrete strain, etc., etc. So those are all other options you can look at for your curves here. And you can define the number of points. So I like looking at generally a larger number of points, something like 100 points in there. And here, your P is where you tell SAP what is the compression force on the column. So we have minus 600. And from my analysis, I saw the maximum curvature here was around 0.003. So SAP will keep going as far as it wants based on those number of points. But you can cut it off so you're not displaying stuff after you have failure, because it doesn't identify, let's say, when failure is. You can just say, go to curvature 0.003. So if you didn't have, let's say, the Excel spreadsheet, you have to identify this just by going and looking through the moment curvature curve on your own. But you can tell SAP here, I have a compression force of minus 600 kips on the column. I have a maximum curvature, in this case, let's say 0.003, just to zoom in on this graph and make sure it's displaying properly. And I get this moment curvature curve, as you see up here. And so you can look, as you scroll up and down this curve, what does the strain profile of the cross-section look like? So you can see, if you have very small amounts of curvature, you have very little strain in the section. But as you move up, you start loading, you start getting more and more and more strain. You can see that when we're at this linear elastic part of the curve, there's not too much change in strain as we're moving up this curve. Very, very small amounts of strain, even though load's increasing very rapidly. You have large increases in your moment. This little curve you see here shows up in a lot of moment curvature curves. It's modeling the rebar a certain way that we haven't talked about. Don't worry too much about that. But as you pass this curve, you start coming back up, and you can see very clearly the strain profile in this section is changing. Okay. So you have, let's say, your compression region on top, you have your tensile region on the bottom. You can also see how your neutral axis depth changes as well. So if we want to compare this with our results, have that middle plot over here. See, they're actually pretty similar between SAP and our hand calc. So I didn't do any parameter studies on this in terms of looking at, is my mesh appropriate or not? But you'd ideally want to do that. And what you can see is, essentially for the very beginning of the curve, these guys are matching identically. We just have that little bit of a difference in how it's solving things from the modeling point of view. But after that, essentially, it just follows our curve pretty close. And so if you look at this difference here, this difference is essentially equal to this drop that we're seeing. So idealistically, if SAP wasn't modeling things this way, they would fall essentially right on top of one another. So I think I'm plotting a little bit farther out there. So the model may actually stop close to that ultimate curvature as well. But generally speaking, you can get a good, let's say, approximation of your moment curvature curve by using these different analysis tools. So when you're using a program like Extract, let's say, you wouldn't have to do this stuff by hand. You wouldn't have to, let's say, do Mander's model by hand or doing these different things. ideally, it'd be working better than SAP, and you could just tell the program, essentially, here's my inputs for my steel, here's the inputs for my concrete, and then I can put the details in, and then it would do, let's say, the development of your effective confinement ratio, and all those different things automatically. And then it would use those as inputs for your stress strain models. So it would generate essentially all this information as well for you ahead of time. And then it would go through and run this whole process where you're looking at curvature, these different increments, and it iterates the compressive strain, and it gives you a section moment capacity based off that variable. And you'll get stuff that, even by doing this discretized fiber modeling, matches pretty closely with SAP.
Are we doing that in this homework?
I'm actually going to push back this next homework for you, so you don't have to worry about this one. Homework 6 will be after the next midterm. I want to spend some more time talking about stuff in SAP here. We can start talking a little bit about stuff here. But I don't want you to spend time on that right now, because if we were meeting Wednesday, I would. But since we're not meeting Wednesday, and then next Monday we're going to be reviewing for your next midterm, I'm just going to push that back until afterwards. Because we'll probably go over PS 231 for a lecture or two over there. We'll talk about setting some stuff up in SAP and doing some modeling that way after the midterm. Any questions on this? And that's essentially how you do moment curvature analysis in SAP. You could then use those properties and some of the different things. Let's see something here. So if you go to find section properties, you go down to hinge properties. Let's say hinge. You have several different options here. So you don't have to necessarily look at a moment curvature response and get a plastic hinge just from moments. You can also have shear hinges and other things like that. Not sure how SAP allows you to model the shear hinges as well. We're not going to necessarily look at that stuff in this class. But if you look at, let's say, this is not the same. There we go. So if you look at these different curves in here, you can essentially give SAP now your moment curvature response in here. So you take that result, and you can tell SAP, I want to form a hinge, and you can assign this hinge to different elements in here. But this hinge then, you basically can look at this stuff in here, and we'll talk about this when we actually start doing a pushover analysis and we put specific values in. But you can tell SAP essentially, I have my 0, 0 point, and then there's a certain point, you'll notice that if you look at the given amount of rotation, there's no change in rotation of the section. But you go from having 0 moment to a value of moment. So this is making use of the rusted hinge analogy, where you have, let's say, no rotation, no plastic rotation, as you're loading your section elastically. But then there's a certain point where suddenly you snap and you go from having no rotation at all to having now plastic rotation. So that's what this first part is modeling. You have 0, 0, and then let's say 1, 0. And so that 1 would correspond to your plastic moment. And then you can define essentially your moment curvature curve, elastic linear, and like I said, there's not too much point talking about that right now, because we haven't gotten into the frame analysis, but that's how you would essentially model this. And so you can go, let's say, moment curvature, give it a plastic hinge length, or you can do moment rotation analysis as well. So you have both those options. And there's another feature in here, I don't think we'll get to any of this stuff in the class, but you can also give SAP what are called limit states. So if you're familiar with performance-based design at all, you can have it identify different limit states in here. So what happens is as you run, let's say, movies of SAP, when it's doing a full analysis, let's say for an earthquake, it'll start color coding different members based on their moment curvature response for a given point in time. So what happens is you can start looking and you can see when plastic hinging forms. So you run an earthquake, you'll see there's no, let's say, nonlinear behavior for the first 12 seconds. Then at second 13, all of a sudden, one of your members becomes color coded. And so you can tell SAP to get different color codes based on different levels of plastic rotation in your section. So you can tell SAP for this given level of plastic rotation, this would correspond to, let's say, first yield of my steel. So I just have the beginning of nonlinear behavior of my steel, and you can see that visually. Or you can set one to correspond to swelling of your concrete, and these would correspond to, let's say, immediate occupancy, life safety, fire prevention, your different metrics that you're using for design. So SAP does have that option as well. But you essentially go in and you define a hinge based off of moment curvature analysis. So that went a little quicker than I thought. Any questions on this? We'll get more into SAP definitely in kind of next block of the class. We do pushover analysis, and we do pushover analysis by hand, and then we start modeling frames in here and take these moment curvature analyses and assign them to sections and things like that. So doing hand and computer calcs for frame analysis. Not very good. Actually, I finished about 10 minutes early today. I will see you guys in next Monday. Yes, Kyle?
So when does homework 5 do? Is it Wednesday or Monday?
We do Monday. I originally wanted to do Wednesday, but I'm not going to be here Wednesday. So no class Wednesday. I'll see you guys next Monday. And you'll turn it in. The test would be a week from Wednesday. No class Wednesday. We'll come back in Monday. We'll do a review for the exam if you guys like. And then we'll take the exam on. Yes.